to talk about padded decomposition, which is a successful work of researchers in France and particularly in Israel. But before that, I want to show you why we are talking about padded decomposition. Random partitioning of a space, random partitioning is the basic, I can say, the basic step for general metric embedding. And for example, one embedding could be f from x to distance of, the metric, d is the metric of that x, and x exclude c, which is a cluster that has x. So I call it Cx. So and it is much more complicated than that, but you see that we need some partitions in order to make some embeddings that has low distortion. But how can we create such a partition? And it is a random partition because random partition over distribution of partitions. For example, this is just one partition. Another partition could be like this. C4 is now bigger. So it's a random event. But we fix that, for example, we fix this partition, which has 4 clusters, and then we talk about the embedding and see how can we prove that this embedding, for example, has less distortion. There are lots of papers, around 50 good articles. I have read around 50 good articles, mainly from researchers in France and Israel. It's so strange that these two countries contribute on metric embedding so much and in a very interesting and deep way. So why do I talk about random partitioning? You may ask that several times, but so now you see why, because it is the basic step for creating such embeddings. And you can create your own embeddings today. And for example, approximate nearest neighbor, you should really read the thesis of Ilya Rosenstein, that if you look at his Google Scholar, he's now in Microsoft. If you read his PhD thesis, it is based on approximate nearest neighbor. His own approach for a more efficient way, and he has described locality sensitive hashing. And one interesting things about his thesis is that he talks about random partitions. For example, there are several ways to create random partitioning. One of them, the method of shortest path decomposition. The other one could be a method called. There are lots of algorithms, but the easiest algorithm that you might think is just locality sensitive hashing, LSH, and I will talk about it. And now you will ask, what is the connection? Okay, to see the connection more efficiently, I should talk about random partitions. I want to talk about approximate nearest neighbor search. So we want to respect small distances. We want to respect large distances. These are very interestingly both interesting for ANN, approximate nearest neighbor search, and also the theory of metric embedding. And so whatever I say is useful for both of these problems. So we want a partition that respects large distances, respects small distances, simple pieces, as small as possible, as Gromov likes in his Hausdorff measure. And that says that, for example, the measure of a Hausdorff is a measure of a Lebesgue over a manifold. So we find a random partition into m parts, and each part has n over m data points. So nearest neighbor friendly random partitions are interestingly dual to sparse cuts in graphs well representable in a metric space. Cutting modulus. So I should write this cutting modulus because both Ilya Reznichtein and that mathematician Naur, I don't know if I spell it correctly, Naur, they have related that to metric embedding in a nice way. So cutting modulus, it is for a metric space M is X and D, the cutting modulus of M and epsilon is the smallest number, which makes the following statement true. For any graph embedded in M with edges of length at most k, I mean any graph such like this, for example, but the edges as at most k, the length is at most k, 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 and all of them the same. And so either there is a ball of radius, so either there is a ball for any of them, either there is a ball of radius k times that modulus that I define, m of epsilon, containing constant number of vertices, or the graph has an epsilon sparse cut. Or if it is not like this, then it is like this. And all of them at most k. At most k. So if that modulus is small, then the metric admits a good data-dependent, locality-sensitive hashing partitions. So the point is, if this modulus is small, then metric admits a good LSH partition. And I will explain what is locality-sensitive hashing. And so let's talk about locality-sensitive hashing. There are maybe more than 20 different versions of locality-sensitive hashing in the literature, but I start with the most classical and oldest method, which is in 1998, goes back to 1998. And so we partition, for example, if I should define that if P minus Q is less than R, so imagine P and Q are 2 points in the Euclidean space, very easy space, then the probability that the random partition of P is equal to random partition of Q is greater than P1. And if P minus Q is greater than CR, then the probability that R of P is equal to R of Q is less than equal to P2. So a random partition is RCR P1 and P2 sensitive? This is the article in 1998. Sensitive if for any P and Q this holds. So we have something like this. This is for R, this is for radius CR, and we have smaller probability P2, and we want higher probability P1. And this is the, distance. And so we get the collision probability. And there are many different ways to partition your space. And I'm a machine learning researcher. So when I talk about data such as images, text, images, financial data, any data, I want to, for example, let's say image. We have a pixel, 1000 to 4 pixels, so around 1000 pixels, and we want to reduce the feature size. So this is a big feature size, so we reduce it. So nowadays in machine learning, some people say sketching, some people say in different contexts, and all of them are talking about the same thing. And the most natural framework is just metric embedding, which is the generalization of any dimension reduction method that you imagine in machine learning. And in future, we will say that all of them are not kernel PCA, but all of them are a different way of metric embedding, and each of them has a different distortion. So we should talk in the language of distortion rather than saying that this one is better than the other one in some case and it is worse in some case. So instead of that subjective talk, we can talk about distortions. And so in the language of machine learning, we can say that we want to partition space. So we have billion images, we want to partition them. For example, image of mine and Elon Musk is, for example, are in the same partition. So we are the same, our face is similar. So we are in partition 1. So in cluster 1, if we have 4 clusters of images. And so there are, as I said, there are many different ways to create this hashing. And by the way, it is all of the research is originated from computer science data structures, theoretical computer science, and so it's so they use data structures, and that's why these ideas are originated from that. So hyperplane LSH, for example, by Charikar 2002, we sample R uniformly. We have 2 points P and Q. We suddenly sample point R, and you see the sign of this inner product R and P. So this is a simple hashing. So the probability that hash of P is equal to hash of Q is 1 minus lambda over P. And alpha is the angle between P and Q, angle between them. And we can generalize to k-hash functions, for example, h1 of P, hk of P, for k is 6, for example. And there's a nice article by Andani and Indik. Indik is an MIT and has many good students such as Andani, and all of them are centered around Indik. And you see how these theories are inspired. We sample TIID standard D-dimensional Gaussian, G1 up to GT, and T could be, for example, 64. So, G3, G2, G1. We want to see which argument from I to T, for example. So basically, I want to say that my hash of a point is argmax of P and Gi. For example, there are some reference images in your image database. You are in machine learning, and you want to partition your images according to this hash. And for T is equal to T, amazingly, it is simply hyperplane LSH. And as T increases, the gap between hyperplane LSH and Voronoi LSH increases. And you see in the proof that why this variable matters. If you read the thesis of Ilya Razinstein for A and N, then you will understand all of these theories. I don't want to waste time on LSH, but it's very interesting. I should say some other things. For example, you should learn cross-polytope, LSH, which uses random rotations, and it is expensive for that. Also, you should read pseudo-random rotations by Island 2009. You should read Hadamard transform, which is an orthogonal map that mixes well and is order of D log D. And I mean, all of these ideas are also used in random projection theory, and so they are equivalent. So I'm talking about both of them at the same time. So the C approximate nearest neighbor can be represented like this. So given a set of points, we construct a data structure such that on query Q will return any point that D of P and Q, this is the metric, is less than C minimum of all metrics, difference between all pairs. And in the original paper in 1998, they defined R1, R2 pleb, which is point location equal balls. And the setup is easy. Given a set P of points of radius R1 and R2, we construct P such that dP and Q is less than R1. We return yes. And any P that P prime and Q is less than equal to R2. So if P is not, if there exists not a P in P such that dP and Q is less than R2, we say no. And I should talk about ball carving. All of them are prerequisites for the next lectures on actual construction of metric embedding. At least it gives you a better intuition. So ball carving is easier to analyze because you have G1, G2, and all of these vectors which are drawn from a normal distribution. It's a d-dimensional vector. So we partition according to, we want to minimize I such that the inner product between these the vectors is greater than equal to eta.